Hello and welcome to my 12th lecture on operating system development. And today I wanted to talk about file systems, or a bit more generally, I wanted to talk about handling data. So obviously you come to a point where you want to load different pieces of software on your operating system, or for example, these pieces of software might require images to display or sounds to play, and so on. And therefore, what you might want to implement is a file system, right? So some organized way to store all of this data. With the usual way of the data being stored as, it's usually being stored as these little collections of related data called files. And those files, these collections of related data, were often stored in sort of higher structures called either folders or directories. I personally prefer the term directory because it's a bit more Unix normative, and I'm a bit more used to Unix operating systems and the IEEE 1003.1. 1003.1 norm, or POSIX, right? So those directories are usually a bit more for a human user. Usually software doesn't really care about that all that much, but yeah. So obviously, if you have studied data structures and algorithms, or you've studied databases, then you probably know that there are different ways to store, all of this sort of data and information relatively efficiently. So one idea that might pop into mind is, pretty much recreating a database, like recreating all of this access to all the different information, using something called a B tree, right? So if you don't know what a B tree is, it's a data structure, but is inspired by binary search trees. So we think of a binary search tree, right? So we know that each node to the right is going to be equal or greater, and every node to the left is going to be lesser, and you can perform fast logarithmic searches. So the idea of a B tree is that each node is actually going to have multiple numbers, and it's going to split into multiple nodes that have values in the ranges that are dictated by the values in that top node, in the parent node, right? And then it has some additional rules, such as the fact that all the leaves must be on the same level, and this basically guarantees that the structure is balanced, elegant, and you can create quite, like some nice recursive solutions for, inserting an element or deleting an element. But the thing is, we're going to be doing none of those today, because we're going to be looking at a very, very simple file system, right? So we're going to be looking at FAT. So there are different file systems, right? So file systems, as I've mentioned, they're the sort of way of organizing data, because, well, fundamentally, whenever you look at any sort of disk, or you look at any sort of mass storage device, it is fundamentally going to be some physical way to encode ones and zeros, right? It's going to be some way to encode ones and zeros. So your goal is to organize the ones and zeros in such a way that software can later use those ones and zeros. So, as I've said, the way this is usually done is by creating some format in which you can define the notion of a file, the notion of a bunch of data potentially in different places being related and that could be used continuously. Well, newer file systems will also add features such as, different access modes to files, or file privileges, file attributes, So, for example, in the NTFS, the New Technology File System, Microsoft Standard File System, you'll see the ACL, the Access Control List, which, if you're familiar with the Unix access control list, the Microsoft one is a bit different. But yeah, you have the extended file system, which is just absolutely beautiful. It actually happens to use B trees, and it has things like journaling, right? And all those are features of newer file systems that are quite desirable. But we're going to stick to a relatively primitive one, which is called FAT, as I mentioned, which stands for File Allocation Table, and that is because we're going to see the entire operating system, the entire file system, is simply going to be based on a certain lookup table called the File Allocation Table, and that is going to dictate something called the cluster chain, which is basically what are the next regions of the disk in which my file will be stored. So the idea of FAT is that we're going to lay our disk down in a specific way. We'll first have a reserved region, and then we'll have our actual file allocation tables. Then we'll have the root directory, and then we will have all of our data. So that's how it's going to be basically laid out. So there are different versions of the FAT file system, such as FAT12, FAT16, FAT32. They're all relatively similar, but I'm going to stick to FAT12 because it's the simplest. But the main difference is the fact that the entries in the file allocation table are going to be n bits in FAT_n, right? So FAT12, each entry in the file allocation table is going to be 12 bits, as we're going to see. So the entire data region is split into clusters. So the idea of clusters, right? So if you've ever formatted a disk into a given file system, right? So you've tried using a software in order to put the disk in such a format that files are seen in this way. You've probably seen a certain option called the allocation unit. Now, the allocation unit is, in other words, the size of one cluster. And the idea of the cluster is, well, imagine if every file, if we had to save, all of the bytes that because, right, we're assuming, our core assumption here is we can place files. One file could be in different regions of the disk, right? And the thing is, if we were to store each and every single address of the byte on the disk, what you don't do anyway, you would store the sector. Because usually you use CHS or LBA addressing if it comes to mass storage devices. But you have like this byte, right, or whatever. And you would have to store each byte or each, sector that it belongs to this file, right? So every sector that the file is saved in, right? So obviously, oftentimes that is not going to be your solution because you would have to save a lot of those sector numbers in which the file is. And anytime it would finish reading a sector, it would have to go, okay, what is the next sector that I have to read in order to get more data from the file? And that is just an optimal. You would have a lot of calls, right? So because of that, instead of splitting into the smallest possible unit, you consider something called a cluster. So a cluster is going to be some collection of sectors, such that we have to ask for another cluster less frequently. right? So we have to ask for the next part of the file less frequently because we will have clusters, which are going to be a bit bigger. Now, there isn't one optimal allocation unit. Obviously, it's going to depend on how big your files are going to be and how many files, if you're going to have one big file or if you'll have many tiny files, right? Because obviously, if you're going to only store a couple big files, then you would want the allocation unit to be relatively big, because that way, it will read one cluster and it will read this giant cluster before it will try to request the next one. But because of the way the clusters work, it's supposed to only contain information from one file. A cluster can contain two files. So if you set a big allocation unit and you have a lot of tiny files, well, they're going to take up way more space, way more artificial space. There's not going to be anything else in the cluster. So you always have to think about the allocation unit in terms of what files are you going to be actually storing on the disk or on the partition, because disks are split into tinier partitions, right? And each partition can have its own file system. Right, so we have those four regions, and as I've said, I haven't said that yet, but if in the reserved region, obviously we're going to have the MBR, the master record, which I've already talked about previously at the beginning of this lecture series, and that is going to be the boot sector, but it's going to follow the MBR norms, so it's going to have a couple extra pieces of information. In fact, one of those, not only in FAT, but also in other file systems like NTFS, right? The New Technology File System, that is also going to appear, and it's something called the bias parameter block, or BPB. So if you check, the documentation of FAT and everything, you'll see what sort of information you're going to have stored in the MBR in the bias parameter block. And a couple of useful bits of information will be, for example, a field called reserved sectors. Because, this is obviously going to tell you how many sectors of the disk are actually reserved or in this region. Now, if you wanted to get this in bytes, then you would have to obviously multiply this by bytes per sector, which is another field in the BPB, the bias parameter block. So reserved sectors time bytes per sector, and this will give you the exact bytes, how many bytes does the reserved section take. However, you don't necessarily need a billion bytes, because as it turns out, it's usually easier to work with sectors when you're talking about mass storage devices rather than bytes. So reserved sectors will tell you the size in sectors of the reserved region. And also in the bias parameter block, you'll have an information called the FAT count. So this is going to tell you how many file allocation tables you actually have in the FATS region, right? So over here, where you actually have file allocation tables, this will tell you how many there are. And another important piece of information is bytes per FAT, which you could actually multiply. And if you were to multiply the FAT count with the bytes per FAT, you would, I don't think that's a field. I think it's sectors per FAT, actually. I apologize. You would get the size in sectors of this entire FATS region. because, well, you just get how many file location tables there are, and you take the size, well, how much does one fat take up, and, well, if you multiply those, you would get the size of the file allocation tables. So then we have root directory entries. So again, in the bias parameter block, you can obtain something called the directory entry count, or root directory entry count. There's going to be some field like this, root directory entry count and directory entry count, right? And each entry in the root directory is going to be always 32 bits. So, yeah. So you have to multiply by 32. No, it's not 32 bits, it's 32 bytes. So you get the size in bytes. So if you wanted to get the size in sectors, you obviously have to divide it by bytes per sector. Because this tells you the amount of entries in the root directory. Each one is 32 bytes. So then to get the amount in sectors, you have to divide by bytes per sector. So yeah, so this is the size of this. This is the size of this. And this is the size of this. Or maybe better visualized, reserved sectors, it would point to the end of reserved, right? And then if you were to add the entire size of the FATS region, you would end up here. And then if you were to add this, you would get the amount of sectors, So in other words, you'd get the LBA address, right, of this data region. So if you add those, at how many sectors does your data region start? So, okay, let's say that we actually want to read some file, right? So this is some disk. Let's call it C. Well, some partition C even. It doesn't have to be a whole disk. And we want to read a file test.txt. So we want to read this file. And, well, we now have to calculate where the root directory entries start on our disk. It would simply be reserved sectors plus fat count times sectors per fat. That would give us the starting sector of this, and the LBA address of this. And you're going to have those entries. Those entries are 32 bytes. And you can consult the FAT documentation. You'll see different fields relating to this file. And the one that is going to interest you is its name. There's going to be some field in this directory entry that is going to be the name of the file. So you read that, and you simply check, hey, is this name equal to test.txt? If yes, then you have found the root directory entry for the file that you're searching for. Well, if it's not the file that you're searching for, you go to the next entry, and then you check again, is this, is the name equal to test.txt? If yes, then you've found your file. If no, you continue to the next root directory entry. And obviously, this is not the most optimal thing to do from a file system perspective, because, this is a linear search. You would think that there is some way to previously organize this data, but for example, make it logarithmic, because linear searches, But you have this test.txt file, so once you've matched the name with one of the name fields from one of the root directory entries, then you'll have to check a different field of the root directory entry. So this was the name, and the information that you want to obtain this is a very strange visualization, but what you want to get is the cluster number, or the cluster ID. To get, actually, let's just leave it as an ambiguous arrow. So you have this name, and you're trying to get the cluster ID. And once you have a cluster, this gives you information about where you can start reading the data. Also, and if you actually check the documentation, if you check the fields of the root directory entry, you'll see that there are actually two fields, cluster low and cluster high, and those obviously represent the high 16 bits of a cluster ID and the low 16 bits. So all the cluster IDs in FAT12, which I'm talking about, are all 12 bits. So we only really care about the low field. Obviously, if you were to do FAT32, you would have to take both into consideration. And they are split apart in the directory entry, so you'll have to combine them yourself with a simple shift and OR. So, yes, so once we have a cluster ID, we'll know where to read the data from. And another thing that we'll know is because, well, we know the first cluster of a file, but as I've said, files are stored in multiple clusters. And this is precisely where the file allocation table comes in. So this file allocation table is a very simple lookup table that tells you about something called a cluster chain. So given the idea of some cluster, you know what the next cluster is that you will have to read. So in FAT12, all of the entries in the file allocation table are 12 bits. Analogously, in FAT16, it would be 16 bits, or in FAT32, it would be 32 bits. And the idea is that those entries, they are indexed from 0. And if you check the entry at the index, which is the ID of the cluster, you will get a number that is the next ID of the cluster that you have to read, right? So as an example, let's say that I have my test.txt file, right? So I've read the bias parameter block from my MBR. I know where my root directory entries are because of all of those computations. And I start reading, 32-byte entry by 32-byte entry. And I check all the fields, and I check if one of them is test.txt. Now, once I've checked this, I get the cluster field. In FAT12, I'll leave the cluster low. And let's say, arbitrarily, this is 3, right? Just some random number, right? So you have this number 3. So you would check the entry in the file allocation table with index 3. Remember, all of them are going to be in FAT12, which is 12 bits. So you read that, and let's say that over there at index 3, right? You have index 3, and it says 4, right? And this means that the next cluster that you will have to read is 4. And in fact, if you want to get the next cluster to read, then you look at the fourth index, or rather index 4, and it will tell you that it's going to be 5. And that's how the cluster chain is going to continue until you reach any hexadecimal value. Well, hexadecimal value, quote unquote. All of them could be theoretically expressed with hexadecimal. But when you reach a value that is FF8 or greater, that is when it's the end of your cluster chain, and therefore you have finished reading the file. So there are no more clusters to read. So that's basically the entire idea of the file system. And but how do you actually read a cluster, right? Well, obviously, I assume that you already have, some, because we've already talked about input and output, so I've talked about, well, I didn't talk precisely, but it's really easy to look up in the documentation how to communicate with an ATA drive, for example. I've seen some people even dabbling with the newer technologies such as NVMe. And you have some way to read and write, so obviously you just need usually the LBA address, right? The logical block address, which is just how many sectors from the beginning of the disk is it, And you usually just need this LBA. If you're using something older, CHS, right? Give a cylinder head and sector. I've talked about those addressing modes also near the beginning of my operating system development lecture series. So we have our cluster, and how do we actually obtain where to read this from the data region, right? Well, we know where our data section starts, and that is because we just perform the sum of all of those, and that's going to be the LBA address of the data region. So let us call that our data offset. And what you simply have to do, also I should mention, this value should always be rounded up. So we have our directory entry count. Yeah, because I mean it could, obviously this division doesn't have to fit exactly, but you'll always need that extra sector. If it doesn't fit, well, you'll waste some space in some sectors. So this is obviously rounded up. So data offset plus, and the cluster ID is always it actually stores a value that is your actual cluster that you have to read from in the data section plus 2. So from the cluster ID, we'll actually have to subtract 2. And then we can simply read the field that is in the bias parameter block, and that is sectors per cluster. So yeah, so the cluster ID, it's the actual cluster ID is supposed to read plus 2, so you have to subtract 2. You see how many sectors are in one cluster, and all of that actually starts from the data offset, because that's in the data region. So for our example, if I wanted to read cluster 3, let's say that my allocation unit would be, I don't know, 4 kilobytes. So that's usually 8 sectors. So it would give me that I have 8 sectors per cluster. So I would have 3 minus 2, so that's 1 times 8. So I have the data offset, which is the LBA address of this. I add 8, and that's the sectors that I'm supposed to read. Obviously, I would have to read in 8 sectors in my example, or whatever your sectors per cluster value is, and you just read that into your random access memory in order to read into memory the cluster of a file of a given cluster ID. So this is basically how FAT12 works. Or actually, well, it's pretty much how FAT works in general. So let's just say FAT. Okay. So this is sort of a simplified example because I've only talked about how to actually read a file that is in the root directory. But obviously we might have a path that is a bit more complicated. So how can we do that? So we have our partition, right? C, and let's say we want access to, I don't know, files, or let's say documents, important, and for example, reports .txt. So how can you read a file like that? Well, the thing is, the thing about directories in FAT is you read them in precisely the same way, the cluster chain that I've talked about. So what you do is you start from here, right? The documents, and you take a look at the root directory entries, and you check just how you checked for a file with the name previously, I don't remember what I've called it, test.txt or something. Just how you looked for that file in the root directory entries, now you're looking for a root directory entry with the name documents. And once you find that, you take its cluster number and you read it in the exact same way as a file. And once you've read it, the directory you've read is going to have the exact same structure as a root directory. So it's going to have those directory entries that are 32 bytes, and they're going to look exactly the same way as the structure of a root directory. So let's say you've read that, right? So you've read that, and now you have, instead of root directory entries, you have documents directory entries. And there you perform a search again. You search for a directory entry that contains the name important. And once you've found the name important, you can load that just like you would load a file. So you take that important entry, or you load it using this cluster chain, and this again is going to have the same directory structure as a root directory. So now you have not the documents directory entries, but the important directory entries. And you take a look at all those directory entries and you compare the names of those directory entries if you can find the name report. And once you have found that name, you simply read the cluster chain, and that's how that's done. So it's actually really easy, surprisingly easy, which it's not the best solution from a theoretical standpoint because you have to physically go for some sort of tree. File systems like the extended file system have sort of tried to tackle that problem a bit differently, but that's outside the scope of this lecture. Yeah, so that is basically how FAT works. So in order to summarize, the file allocation table file system splits the disk into 4 fundamental regions. Reserved, which is going to always contain the MBR and the master boot record, which contains the BPB or the bias parameter block, which contains fields according to the commutation we can read where at a specific offset, such as reserved sectors, that is going to tell you how many sectors are in this reserved region. Then, in order to get the side of the file allocation tables, you take the fat count, or how many fats there are, times how many sectors one fat takes up. And then you can take the amount of root directory entries, you multiply that by 32, because one of those entries takes up 32 bytes, and you divide that by bytes per sector in order to get the sector count. Obviously rounded up, because you can't have one less sector. Let's say, right, that you needed 4.3 sectors for that. You can't have something like that, but you can have 4 sectors because it would have some data missing, so you have to round it up to 5. So then, you know all of this information, so once you actually want to read a file, right, you simply take the name of the file, or, well, if it's a folder, you're going to take the name of the folder. You'll actually iterate for all the root directory entries, but you know where they are because you know the offset at which the root region is. You go for all the directory entries and you check all their fields, according to the documentation, and you see where the name field is. You check if the name field matches with the name of what you're searching for. And if it matches, you take a look at the cluster data, and then you can obtain, you can actually read, the data of this cluster by reading sectors per cluster sectors, right? Because that's how many sectors you'll have to read in order to read one cluster. From the offset, data offset, which is just all those things, summed, plus cluster minus 2, because the cluster ID is actually higher by 2 than what you're supposed to actually read, times sectors per cluster, so how many sectors you have to move in order to get to the next cluster. So you read from this offset the amount of sectors that is in a single cluster, and once you've done that, if you want to read the next cluster, you check the index in the file allocation table that is your cluster. So for example, row 3, you check what is in row 3, and each entry is, well, in fact 12 bits and 16 bits and so on, right? You read that, you have the ID of the next cluster, so you can read that, and once you've done that, you can see what's in the next cluster, read that, see what's in the next cluster, and once you reach a value that is FF8 or higher in FAT12, then that's basically when you'll have to terminate, because you've read the whole thing. And when you read a whole path, right, then you simply read a folder like it's a file, and this quote-unquote file is going to have the same structures of the directory entries as the root directory entries. Okay. So, that is everything I wanted to talk about if it comes to file systems. So, I hope that I have given some ideas about how the file allocation table file system works and how files can generally be stored on a computer disk. So thank you very much for watching, and the next lectures will be really interesting because, well, this just ticked one of the marks in the requirements that I listed in my first lecture, and that is data, because now we have some way to handle data. So now I will be talking finally about scheduling, and I'll be talking about scheduling user space processes. So we'll talk a bit about the user space, we will talk about processes, deadlocks, scheduling, synchronization primitives, threads, and then, we'll slowly go towards the end of this series, and we'll have created a relatively well, maybe not a relatively good operating system, but it will be at least a piece of software that one can call an operating system. It will run processes and manage the resources. Thank you for watching.